G'day Internet and welcome to GameDev Coaching episode 45. This is the third out of 3 episodes that I'm needing to re-record because my hard drive died and it took 3 episodes with Daniel with it. So I'm just going to be on my own talking through what we did in this episode. So in this episode, you recall last time we started, we finished with being able to drag shapes around just by placing them somewhere. And so in this episode we want to add the concept of it like a spring, if you've ever played with most physics simulations, rather than just immediately dragging shapes, you'll actually drag them with a little spring between the shapes. So let's get straight into it. So let's see, what do we want to do? We want the shapes to be able to move over time, and so that means velocity, so distance over time, meters per second, public vector to velocity. So now we have the speed, or I guess the velocity that these shapes are moving with, and we want a system of continuous updates. So we also want to add the concept of, I'm working on Daniel's version of the code, or the version from the last 2 episodes, so slightly different order to what I have in my file. That's fine. Bool pause. So we do actually want to be able to pause the simulation. So we're going to have a system of continuous updates. So it's going to update every frame unless we pause it. So and then we might want to, we'll leave that for now. So we could look at the separation system, but for now we'll just leave it. So I'm going to add a simulation block to update, and this is going to let us move things around. So so this is like our game loop. So, and if it's oh look, it auto corrected that. If not paused, we're going to do that, and if it is paused, we'll do something else. So let's add a really simple way to evaluate velocity. So we talked about this is Euler's method, I think. Yeah. I've forgotten all my terminology that I checked for actually doing it the first time. So anyway, so this is we started by doing the silly way of updating shapes. So we're going to go shapes. So for every shape, we're going to update all of them. Shape count shapes I dot position plus equals shapes I dot velocity times delta time. Now we need delta time, so we already have this kind of concept of delta time. And let's just go and look at where that has run off to. I swear we had it. I'll just grab it out of the other document if I can find it. Here we go. So this comes in handy a lot of the time. Oh, this version of the code doesn't even have our... yeah, that's annoying. Oh, well, I have the new version of the code. Okay, so working on a slightly older version of the code. So you recall that the new version of the code has, let me see if I can find it in the one on my second monitor. It's got this thing here. When we hit space, we increase time. And so is that going to tell me that time doesn't exist? So yeah, and then delta time we set at the very top of the update method. Or we took delta time that out and we made our own variable, because delta time comes in handy. So it's like, here's the input in the mouse state. So are we using mouse state anymore? We are a bit, so I won't remove it quite yet. So this is just one of the sort of key components. So you recall we had this time thing, and then you hit the spacebar and the shapes went wee on their own. So I'm just going to skip over that for now. We'll pretend that doesn't exist, but in our code that we actually did, we actually integrated these things together, so they you could use both at once. I think something like that. So anyway, if you're watching this and playing along at home, I do apologize that the code is somewhat out of sync, but what are you going to do? Okay, so we're evaluating the velocity, and so we need to set a velocity. And we'll just set a velocity when we place it. So pending shape. So we're position vertices. Shape count. Equals dot velocity equals new vector 2. Let's call it 5.0f 0f. And so in theory, we do this for both circles and rectangles. If we now place a shape, oh, it's moving off to the side, and we can pause it. We should probably add in a pause and unpause mechanism. If input dot key went down, keys dot enter, pause equals not paused. So now I can pause it, unpause it. Off it goes to the side. I can pause it and unpause it. So the shape's moving around by time. So then you know, we want to add gravity to the situation. So if you recall our formulas, let me just copy it in from the other document because that's easy enough. So we had okay. So we have the position equals well, this is the formula for velocity, is we're adding acceleration. So this is a silly way of doing it. We update velocity equals acceleration. So we know that acceleration and gravity, we don't have gravity in here. So new vector 2, 0, 9.8 meters per second. So we're working in meters per second. Did I even zoom out this one? So another thing we did in a previous episode was we changed the default zoom level to, where is it? Zoom out, zoom level. It was 12. So we zoom in a bit so that we're in a reasonable scale. So now a gravity of 9.8 meters per second is sort of looks sensible on screen. So and just slowly resyncing these files. Never mind. So oh look, and another thing we did in another episode was we made sure that the camera pointed in the correct direction. So no, we actually did that. I've just set gravity to go up. So always good to check your direction. So now, as we can see, we make a shape and it moves down. So with gravity. So this is what we learned was the analytical method of I think analytical is the right word. This is the formula for the position for a static starting point, but we're going to be changing the velocity and stuff as we go. Unfortunately, I'm a little bit annoyed that I've don't have the code to compare it to, but that's fine. I'll copy it in. So we want a velocity for testing. So rather than using this velocity that we set here, I'll just copy the code that we wanted. So this is the code that we wrote in a previous episode. Continuity has just gone completely out of the window. So let me just find it. Velocity to hit. So this is the velocity to hit method. This is my version of it. So which has a dirty great comment in it saying get Daniel's version of it because it's slightly better. I'm just going to paste it in here. So this is something that we wrote in a previous episode. So rather than setting our velocity to hit, rather than setting our velocity based on just this fixed value, I'm going to set it to 0. And then when we hit a button, we're going to set the velocity of every single shape. So if input dot key went down, keys dot v I think we used, we're going to set velocity to hit for every single shape. Shape, we're trying to hit the world mouse position of shape. See, I think we actually could get rid of that, and let's make a variable gravity Please fix that, thank you. Okay, so I'm just going to throw together something for gravity and vector. Okay, so gravity, don't mind me as I sort of throw this together. All right, gravity, so, and now we need to set this to something, so dot y, so yeah, it's a little bit thrown together, it's fine. Okay, so we're setting the velocity to the velocity of hit that we wrote in the other episode that goes before this one. So now if we zoom out, we can then hit V and the shape starts to come towards the cursor. Now, it's very hard to see, but it's actually not quite hitting the cursor position. We can add some more shapes and they all will try and head towards the cursor there. But you'll notice that they're not quite hitting where they're supposed to. They're not quite hitting the center, and the reason for that is we've used this Euler's method of incrementing the thing. And I'm going to bring up the old whiteboard. So this is the whiteboard that was in the episode video that we lost, and so I've explained this before in a previous episode. So we have this nice curve here in green, and that's where we should end up for the position. But if we do it stepwise, so we've got red, 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 and these are straight lines. I know the diagram's not great. So this is a curve, and this is straight lines, and we're basically accumulating error here. Let me see if I can bring up the Wikipedia. If this is going to give me a diagram, here we go. So this is the same diagram here that I showed on Wikipedia. So this is what we expect to get, but if we evaluate it at fixed time steps, we end up getting that red line. So we can actually fix this in this case by changing to this formula here. So we're going to change the position. We're going to evaluate this first because obviously u and sort of u becomes v. So we want the initial velocity at the start of the frame, but at the end of the frame we want to have the final velocity. So we're going to set the position first. So we don't have to have temporary space velocity. So we don't have to have a temporary space velocity. So all we need to do is add. So this is the component that ended up being missing, 0.5 f times acceleration, which is gravity, times delta time times delta time. And this is why we put delta time in another variable, because you can see we're starting to use it a whole bunch. And then velocity equals just the initial velocity plus gravity times delta time. So this is now properly integrated, and it will still accumulate. Oh, I'm going to turn that off too. So that was because we've now zoomed in to make the thing sensible. So another thing that we changed just along the way, this is something interesting about code, that is it accumulates little fixes as you go. So now we don't have a minimum size. So okay, so now when we set this, they should all hit exactly in the center, and they do, just trust me. There will be some error due to like floating point error accumulation, but it's not like the larger error of Euler's method error due to missing this entire section of the formula, basically over each time step. So that's there. We have a velocity. We have a velocity to test it with, and now we have a velocity. We want to implement a spring to drag stuff around. So let's just So I'm going to turn off gravity for now. So what I'm going to do that is we'll use gravity equals false to begin with. So, and this just becomes really convenient. Sorry, vector 2 acceleration equals vector 2.0. If use gravity, I'm going to add f equals gravity. So that just lets us turn off gravity, which is going to be really handy for now, because we don't actually, when we drag these shapes around with the simulation, we don't want them moving. Another thing we're going to do is I'm going to change the way this is handled. So I'm going to remove this code from the unpaused path. So when you pause it, we can, we don't need that, sorry. When you pause it, you can still move it as normal. So if else, so this is paused, if shape being dragged, just make 1. So we don't want to be able to drag around shapes in a conventional way while the simulation is running. We want to use the spring, so you can see that it's not being dragged around. We want to turn that into a spring and add some velocity, but if we pause it, other way around, no, enable editing, thank you, is not equal to -1. Really? Okay. Try again. So if I pause it and then I can drag it around, just using the normal method, but while we're unpaused, while we're simulating, I want to use the simulated method with a spring. So let's talk about spring physics. What else did we do? We did have a long discussion about how we derived this. So that's just revision of this formula. So go back and check previous episodes for this and how integration works and how we ended up with that by integrating acceleration and then velocity to get position. Then we have Hooke's law. And so basically what this is, we have a shape, this green rectangle here, and we have a spring coming off it. And the distance between the point that we grabbed and the point that we're dragging to is where the spring is, and the x is the length of the spring. Or at least x is the difference between the natural length of the spring and the actual current length of the spring. So we're using a spring that we want to be 0 lengths, as in we want to, when the system is at rest, we want the spring position here to be on this position. So x is always just the size of the spring. So we're trying to reduce that down to 0. So we have Hooke's law, and the force of the spring is equal to the negative spring constant times the distance that the spring is traveling. So we have this formula for force here, and we also know, what's this, Newton's law? Can't remember now. Force is equal to mass times acceleration. And so we can do a little bit of algebra over here and just swing this formula around, and we get acceleration equals the force of the spring divided by mass. So this is just a bit of algebra, and so we reviewed that, and that's Hooke's law. And we'll come into what the rest of this is in a moment. So let me just find my reference code. Okay, so we have acceleration with gravity, which we can turn on and off, and we actually I'll just demonstrate that, because so if I unpause it, I'm sorry, if I so let me just check this is doing what I expect it to do. This is why we always test code. So we're paused. Sorry, we're unpaused. Why are we not moving? Shape position, shape velocity. Acceleration should be acceleration due to gravity. Are we ticking? Why are we not ticking? So let's find out what's going on here. Use gravity. It's false. Oh, I turned off gravity, so I'm keep pausing and unpausing and expecting to turn gravity on and off as well. Let's turn on gravity. There we go. I don't even have a key for gravity. Okay. I'm trying to do this sort of quickly and sort of on the fly. So gravity equal, use gravity. Try this again. Okay, so I did want to show this, that I can turn gravity on and then, it doesn't move, but when I pause it, then I can drag it around. That looked like it was actually slightly bugged. Oh well. Anyway, doesn't matter. We'll move on to what we're going to do. So we just looked at Hooke's law on the whiteboard. We have this little formula here, so I'm just going to add it in. So if shape being dragged is equal to I, so if we're dragging the shape that we're updating at the moment, we want to add in some acceleration. So this is the spring constant, and I'm going to use a number that I found through experimentation earlier, but this is a thing that we can tune. So this is the stiffness of the spring. And in fact, I may actually go in and tune it a bit. So x equals, now we want the distance between the world position, mouse world position, and the shape. So this is the value we're trying to reduce down to 0. So, and this is actually a two-dimensional vector. So shapes position minus shape drag offset. So you remember we actually drew this shape position minus shape drag offset. We drew this, I think, last episode down here. So this is shape minus shape drag offset, gives us the position of the shape that we want. And then minus mouse world position, that's that. And then acceleration plus equals k times x, sorry, k times x divided by and then mass. So I kind of gloss over what the m was here. So a force is equal to the mass times the acceleration. That is the amount of force being applied, or the force you need to apply to accelerate a mass by some amount. So acceleration equals force divided by mass. And we fortunately have a way to get mass, so get mass, and get mass of the shapes I. And so now, hopefully, I can drag this around with a spring, and you'll notice if I hold the button down, it kind of oscillates around the spring. And this is not exactly the behavior we want necessarily, although this could be useful. So this is where the other thing came in on the whiteboard. So this is the other part. So we have a dampening effect, so the force of friction. And this is a really simplified frictional force, but it's good enough for our uses. And what friction is it's relative to the velocities. So it's basically some factor, some negative factor, so it's a retarding factor multiplied by the velocity. So the faster you go, the more friction you have. And so we're just going to add that in. So we end up, again, we have a force, so we can use force equals mass times acceleration and some algebra to end up with the force that we want is the force of the spring plus the dampening force is equal to negative kx minus bv equals the mass times acceleration. Then we just pull that mass down there and divide by it, and we end up with acceleration equals the spring constant times the distance minus the damping constant times the velocity, all divided by mass. And so we're just going to put that in there too. So b is the damping constant equals minus 8. Again, this is a value that I got through experimentation, but we'll play with that in a moment. In fact, why don't we play with that now real quick. So just to demonstrate, if I put a thing here, you know, it's oscillating like that. Now if I change this up to like a 100 stiffness spring, you'll see it moves a lot faster. Whereas if I change that to like a 1 and move it, you'll notice it moves very slowly. So I found that 40 was about the right value. So then we have the damping constant, and we can play with that as well. So plus the damping constant times the shape dot velocity. So relative to the velocity. And you'll notice that the system slowly settles down. And so if I were to say, let's increase the damping constant, so like 100, let's draw that now. And so it's a really stiff spring, and it takes a long time to settle back to the position where we've dragged it to, whereas the other one was oscillating a bit, so maybe it wasn't strong enough. Whereas if I set it to 1, then it's basically having no effect, so or having almost no effect, and we still get that oscillation. It's going to take a really long time to settle. So that is basically the spring dragging method that we made. And so one of the reasons this tuning is a bit off, so when you're making a system that is designed for user interactivity in a physics simulation system, you generally want your shapes, like if you've got the God hand here, like the user, you'll notice this shape has a lot more mass, it's got a lot more inertia. It takes a really long time to move around, whereas this one, you know, you can swing it around quite easily. And that's fine if you're like making a realistic physics simulation, but when you're making user interactivity, that's actually annoying. So what we can do is we can get rid of this mass term, and then effectively shapes of like vastly different sizes will feel about the same. You'll notice that the tuning that I came up with earlier is actually a lot more pleasant for that as well. They kind of settle and don't oscillate too much. But it's still, you can still fling things around, which is useful if you want to set some velocities. Now, if you're in a someone else's physics simulation and you want to do this, you'll notice that sort of algebraically, if you force to have this divided by a mass term, you can actually get the same effect by if you multiply both of these parts of the formula by the mass, which you can do by setting the constant appropriately. The damping and the velocity constant appropriately, you get the same effect, although you then have to calculate mass extra times. Although the fact that we're constantly calculating the mass, you know, we could cache that if we were so inclined. Anyway, that's some discussion for that. I'm going to take that out. And then the final thing to talk about, we drew the spring line, we've got damping. Okay, we made the spring feel good. Okay, so the final thing to talk about, and this was just a bit of a discussion, this is not something we actually got into. This is the other layer of the thing. So this is our formula for motion. And so one way of calculating this was, you know, velocity plus equals acceleration and position plus equals velocity times time in both cases. Or we can do it the more sensible way. And this is good because we can just integrate up. So we can integrate acceleration to get velocity, and then we can integrate velocity to get position. And this was just showing Daniel the notation. So it's acceleration equals the double derivative of the position. So obviously derivative is the opposite of integration. So this is equal to just like the position derivative and in brackets and then derivative again. And this is all well and good. This is something we can calculate directly because acceleration is constant. And the initial velocity is also constant. So this is actually easy to calculate. However, what we have here is called an ordinary differential equation, and this is the spring equation. So, and I kind of played a little bit fast and loose, like I got rid of the terms for like I got rid of s becomes x. So just pretend x is distance. Same s is here. So this is s and x aren't really equal as such, but we're going to pretend they're basically the same thing. It's the same order of thing. It's a position of some description. And you have this equation here where you're relating the position to the first derivative of the position, or the velocity, and the second derivative of the position. And if you rearrange that, you get this ordinary differential equation. So 0 equals negative kx times x, minus something times the first derivative of x minus the second derivative of x. And what's this in red? I think I think that was a vague attempt to explain the fact that s and x are not quite the same thing. But anyway, so we were using Euler's method before, and we had a problem but then we just went and solved it directly and got that. You can't solve this directly particularly easily and get a thing that calculates the position for any particular time, but you can use more complicated versions of Euler's method, which are the Runge-Kutta methods. Let me see if I have the Wikipedia page up. So the Runge-Kutta method, and I'll bring up this diagram on Wikipedia that we showed, so you can see in, I think, red is the exact value, and here we have, unfortunately it's in like Swedish or something, but I think Runge-Kutta is this yellow one, and that gets very, very close to what we want, whereas a plain Euler's method gets, there's this massive difference between the value we actually want, the exact value, and what we calculated numerically. And you'll see this blue one is Euler half step, so you see they've got an extra step in between, and that gets a little more accurate, but it's really not as good as actually just either calculating it directly or using a more sophisticated integrator like Runge-Kutta. Now, we didn't actually get into what the Runge-Kutta methods are, because we're not really, like, that's a level of accuracy we're not caring about at the moment, but we may eventually, if accuracy becomes a problem, we'll look at it. But it's just something that I wanted to add in so that Daniel and everyone watching has an awareness of what it means. The other thing that I wanted to talk about, there was one more thing. That's right. So Daniel pointed out that can we calculate this exactly? Like, can we plug this into Wolfram Alpha, which is what we use? So it's like I think let me see if I can do this on the fly. So integrate A with respect to t. Is that going to, okay, so that's going to give acceleration times time plus a constant, which is our starting acceleration. So that gives us velocity. Yeah, sorry, plus constant, which has our starting velocity. So this is velocity. And then if I integrate it again, I should get position, and this should be our formula we had before. If it's not going to let me do that. So, well, let's see. Let's AT with respect to t. Let's just copy that formula here. AT plus u with respect to t. This is going to give us our S formula from before. So we've got half AT squared plus the initial velocity times time. So this is our S formula from before. But now what happens if we then plug in our ordinary differential equation? So, and what we found out is that Wolfram Alpha will actually calculate this for us properly. So 0 equals negative kx minus bx derivative minus x double derivative. And so if we plug that in, then Wolfram Alpha will think for a while, and it will tell us that the exact calculation of x is a second order linear ordinary differential equation, and you can actually solve it if you were so inclined, and this is the result. So the offset at time t is equal to constant 1 to e to the half t, blah, 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 with a square root in here and so on. And you can see why this sort of formula is something you don't want to get too deeply involved with, particularly because this is going to be a problem, because as soon as you move the mouse, you have to do it in a stepwise way anyway. You've got square roots and stuff in there, whereas before all we were doing is like some addition and some multiplication. I guess a little bit of division for the mass, but you can pre-calculate inverse mass. So this is not something you want to do in most circumstances, but it is available. You can actually calculate exactly the behavior of this spring at any point in time. It's just really messy, and not something you want to focus too hard on. So anyway, so that's everything we did in episode 45, I believe, and so now we've already done episode 46, so I've had to actually come back and re-record this. after. My right mouse button's failing. So yeah, I've done this re-recording after we recorded episode 46, so you'll see a little continuity gap there again, unfortunately, but such is life. So anyway, thanks for watching, and again, sorry about the problems that we've had with the lost episodes, but hopefully going over it like this is enough information to get everyone caught up on what we did. So yeah, I'll see you next time.